What's up, guys? Welcome back. Patrick here. Moving on to the next video, still dealing with L'Hopital's rule. We're now going to talk about indeterminate differences. And indeterminate differences is just a different type of indeterminate form. So to do a quick little review of what we've covered so far, we've been talking about indeterminate forms. And so far we covered indeterminate quotients. And that's when we have a limit in one of two formats, plus or minus infinity over plus or minus infinity, or if we have 0 over 0. We've also dealt with indeterminate products. That's if we have plus or minus infinity times 0, or 0 times plus or minus infinity. And now, in this next set of videos, we're going to talk about indeterminate differences. And indeterminate differences is one of two formats. So you'll either have positive infinity minus positive infinity, or you'll have negative infinity minus negative infinity, like that. And so notice that if you got two functions like this, you can't tell what's happening. You don't know if this one's going to positive infinity quicker than this one, or if they're going to compromise at a certain number, right? So one of these two formats, you can't tell what's happening. You're going to have to apply some kind of different strategy. Now, before we talk about the strategies, what I want to mention is that notice that we can't have, for example, positive infinity minus negative infinity. Okay, this is really important because if you have this, what this is going to end up being is just positive infinity plus positive infinity, right? That negative negative turned into a positive, which is just going to give you positive infinity. So you know that that limit's going to go towards positive infinity. Now if you had negative infinity, let's say minus positive infinity, then this would be negative infinity minus infinity, which would give you negative infinity. So you know that limit would go towards negative infinity. These are not, this and this are not indeterminate differences. It has to be one of these two formats, and that's super important. We're going to go over an example of where we take a function and just a small change in it can go from an indeterminate difference to not being an indeterminate form in one of these formats here, right? So you got to be careful with these limits that you're going to be dealing with. You got to make sure it's in one of these formats. And same for these indeterminate forms too. You got to make sure it's in one of these formats, not like positive infinity over 0, for example. That wouldn't be an indeterminate form. Now, if you remember with indeterminate products, what we did was we sort of manipulated these and put them as indeterminate quotients, and then we were able to apply L'Hopital's rule. With indeterminate differences, it's going to be a little bit trickier. There's not going to be as much of a pattern as there was with indeterminate products. There's actually going to be three main ways to deal with these. Either you're going to have to get a common denominator, another way is going to be with rationalization. We're going to go over all of these. We're going to go over examples that cover all of these. Rationalization. Another way is going to be to take out a common factor. Those are the three main methods of how you deal with indeterminate differences. And sometimes these methods will lead you to have an indeterminate quotient. Then you could apply L'Hopital's rule. But sometimes it won't. Sometimes you're going to have to sort of deal or use other techniques that we've dealt with previously in the course with limits. So indeterminate differences, there's a lot of different scenarios that could come up. But I'm going to go over a bunch of examples. I'm going to go over these three methods right there. So let's do an example here to see how indeterminate differences work. So let's say we got the limit as x approaches pi over 2 from the positive side of tan x minus secant x. Now, what you want to do is do a direct substitution to see what is happening with the function that you're given. So let's start off with tan x. Now, tan x, if you remember the way it looks, is like that, right? Where this here is going to be at pi, and then this is going to be at 3 pi over 2. So notice that as we approach an x value of pi over 2, this is tan x, from the positive side, notice that the function is going to go towards negative infinity. So this here is going to be negative infinity, and then we're going to be subtracting secant x. Now what's happening with secant x as x goes towards pi over 2 from the positive side? Well, secant x we can rewrite as 1 over cos x, and then cos x looks like that. This is cos x here, and pi over 2 is right over here. So as we approach pi over 2 from the positive side, we're going to have a very small, the function cos x is going to go towards 0, but it's going to go towards 0 from the negative side. So basically this denominator here is going to be a very small negative number. So 1 divided by a very small negative number is going to give you negative infinity. So secant x is going towards negative infinity as x goes towards pi over 2 from the positive side. If it was going from the negative side, then this would be a very small positive number here. 1 divided by that, that would give you positive infinity. So we know secant x is going towards negative infinity. You could have also maybe drawn the graph for secant x, but if you don't want to remember as many graphs in your head, you just want to deal with maybe taking the reciprocal functions and then changing them to have the primary trig functions within them, then you could just see from here that as we approach pi over 2 from the positive side, that function is going towards negative infinity. Right? So notice that we got negative infinity minus negative infinity. And that is one of the indeterminate difference forms. And so we can't do a direct substitution. We got to use a different method. Now, what we can do with this here is we can actually change these. So the tan x we could change to sin x over cos x, and then the secant x would be 1 over cos x. And now notice that these two have a common denominator. Remember that was one of the methods we went over? And so what we're going to do is we're going to take these two expressions and change them to one expression. So we would have sin x minus 1 over cos x, like that. So we took these two expressions, changed them to this one expression using a common denominator. So that method of a common denominator, that's usually what's happening. You're taking multiple expressions, changing them into one. And now notice if we do a direct substitution on this, as x approaches pi over 2, sin x is going to approach 1, right? Sin of pi over 2 is 1. 1 minus 1 is 0. And then cos of pi over 2 is 0 as well. So notice now it's an indeterminate quotient, right? So we took an indeterminate difference and then changed it to be an indeterminate quotient, and it's still the same function. But what's nice now is that because it's an indeterminate quotient, we could apply L'Hopital's rule. So if we do that, what we would do is take the derivative of the top, so that would be cos x, the derivative of the bottom, negative sin x, and now we could do a direct substitution. We'd end up getting 0 over negative 1. Right? Cos of pi over 2 is 0, sine of pi over 2 is 1, and then we've got the negative in front. Then 0 divided by negative 1 is just 0. All right, so that's the answer to this limit. So we took that indeterminate difference, Common denominator, changed it to be one expression here, and then this was an indeterminate quotient. Then we applied L'Hopital's rule, and then we got the final answer.